again, we're talking about the air pollution control engineering, and this is basically our class time and office hours. So I think we have everyone here in the class, so let's do a quiz about the contents last class, right? So which one of the following is not a criteria air pollutant? So I'll launch this quiz problem. So we learned 6 criteria air pollutant. Okay, so to save some time, I'll just end here and I'll share the results, okay? So it should be carbon dioxide, right? So we know that the 6 criteria air pollutants are basically PM. We said this is also particulate matter, right? PM, sulfur dioxide, nitrogen dioxide, carbon monoxide, lead, and ozone, okay? Therefore, the carbon dioxide is not a criteria air pollutant, okay? So we'll also introduce that even among these 6 criteria air pollutants, we can categorize them to primary air pollutants and secondary air pollutants. So primary air pollutant just means that they're emitted directly from, for example, the combustion process or from the human activities, right? So the first 5 are the primary air pollutants, right? They're formed directly, but see. Yeah, but for the ozone, it has to be formed indirectly. For example, it's formed based on the reaction of the nitrogen oxides or the VOCs, right? It's not being directly emitted. That's why we also cannot evaluate the emission rate of the ozone because it's not formed directly, okay? So this is a quick recap of our last class. So we mentioned that actually EPA has standards for or have some regulations regarding these air pollutants, right? And actually this table shows the required level of these air pollutants. So basically it's set, it gives out these standards. So if the concentration of these air pollutants are above these required levels, we can say that the air is pollutant. It's going to be bad for human health. So you see again, we're talking about 6 criteria air pollutants, right? We have carbon, we have PM, right? We have sulfur dioxide, nitrogen dioxide, carbon monoxide, lead, and ozone. Okay, so all 6 of them. So in terms of the level, it's basically the concentration. So you see, for carbon monoxide, let's say, actually have 2 different levels. One is 9 ppm, one is 35 ppm. So ppm means parts per million. So 9 ppm just means that among 1 million of the air molecules, so the air molecules also include these carbon monoxide, right? So all of these gas species. So there are 9 molecules of carbon monoxide. So 9 ppm just means that among 1 million of the air molecules, there are 9 molecules of carbon monoxide. Okay, so following this ppm, following this concentration here, you can also see a mass concentration. So ppm just means the mole fraction, right? So what is the number fraction of these carbon monoxide molecules among all the air molecules? So following that, we also have a mass concentration. So these are basically different metrics of describing these air quality standards. And we can later find out that these 2 are actually equal to each other. We can do some simple calculation to show that. So the reason why we're setting up two different level or two different standards is based on its averaging time. Okay. So the averaging time means how long we do these measurement, we do this monitoring. So for example, so 9 ppm, that's going to be 8 hours average. 35 ppm, that's going to be 1 hour average. So what does that mean? Let's say EPA sent some person to monitor the air quality on our campus, right? So they're gonna set up their carbon monoxide monitor, let's say in front of our building, right? It's gonna be outside ambient air. So let's say this person have limited time. He or she can only measure for 1 hour. So in this case, the air quality standard is gonna be 35 ppm. But if he or she has longer time to monitor the air, then the level is going to be 9 ppm. Okay, so why is that the case? Why is it not reversed? Let's say 8 hours is going to be higher concentration, 1 hour is going to be lower concentration. Why is that not the case? So this really involves the fluctuation of these air pollutants, right? So let's say we're measuring the air quality. I remember there used to be a power plant on our campus, right? So that also generates air pollutants. Let's say we just measure the air quality there. So also, let's assume that the power plant only turns on, they only run that during the morning, for example, 10 a.m., okay? So what we're going to see, let's say the CO concentration as a function of time, is we're going to see a spike of the CO during that time, right? And then it might come down, right, for the rest of the time. So let's say if the person came in and monitored the air quality just right during this time, okay, so we're definitely going to see a higher concentration of the carbon monoxide. And because of that, people set up a higher standard. Let's say as long as this spike, the average concentration is below 35 ppm, we'll still say that it satisfies the air standard. This is considering the spikes of the concentration. But if the measurement is long enough, let's say can continue for a longer time, 8 hours, then we know that the average concentration will of course be lower, although higher than the background, but lower than this highest concentration of the spike. So that's why for longer averaging time, we're going to see, or we're going to use a lower standard here. So as long as it's below 9 ppm, we'll say that the air quality is good. So this applies for all different types of air pollutants. For example, for nitrogen dioxide, you can see that we have the annual arithmetic mean, right? Annual mean, and also 1 hour mean. So you can see the annual mean is much lower compared to the 1 hour mean. So same for sulfur dioxide. They even have the 3 hour, like say 24 hour, 3 hour, and annual mean, right? Same for carbon, same for the particulate matter, right? So that's why we're going to use different standards in terms of the air quality, right? We have to consider what is the dynamics going on in these air pollutants. Okay? So we'll come back to this table to show why these units or why these metrics are equal to each other, because they have to be equal. Otherwise, let's say some industries or some people will always use the higher standard, right? Basically, that's going to save a lot of money in terms of removing these air pollutants. So as we mentioned, air pollution as a topic, basically this phenomena doesn't happen by itself. It always involves human activity, because just by nature itself, they're not going to create air pollution there, right? So here I'm just going to give you two examples of air pollution, and also these are basically as people's knowledge grow, some species, gas species that were regarded as not an air pollutant may become an air pollutant as time goes on. So the first example is the ozone depletion, okay? So people say that the ozone depletion is a huge problem for our Earth, right? But if you think back, if we look at the criteria air pollutant, ozone is one of them, right? So if we have ozone depletion, that should be a good thing, right? So why is it an air pollution problem? So it really depends on where the air pollution is taking, where the ozone are at. Okay, so ozone is at a different location of the Earth. They might be beneficial to humans. So if we have ozone depletion at certain location of the world, that's going to cause the air pollution, or that's going to cause negative effect to human beings. So, so let's say if we draw a schematic of our Earth, so we have the Americas, Asia, Europe, and then we have the Africa, Australia, right? We have the Antarctica, okay? So this is our Earth, all right? So when we say ozone is an air pollutant, we're talking about a layer of air that's around 10 kilometers high. So we call this layer of air or layer of atmosphere as a troposphere. So I'm pretty sure that almost all of the people live in this layer of air, right? Except for astronauts, okay? So above this layer of troposphere, there's another layer. It's called the stratosphere, which can extend a little bit higher. So inside the troposphere, the air is well mixed. Let's say if we have a power plant sitting up here, and it's emitting ozone, or emitting, let's say, carbon dioxide, NOx, VOC, right? So these gas species can go through reaction to form ozone, right? So the air inside this troposphere is quite well mixed. That's why if we are having pollution taking place at one location, the pollutants will be able to travel across the continent or even around the globe, right? So in this case, if we have ozone in the troposphere, that is an air pollutant. That's going to cause asthma. If it's inhaled, it's going to cause some allergy or some diseases to human beings. But ozone also exists in the stratosphere. And normally there is limited air transport between the troposphere and stratosphere. It's very difficult for ozone to escape into the higher, the other layer of the atmosphere, and also it's difficult for ozone to transport down to the surface of the Earth. Okay, so when we talk about ozone depletion, we're talking about the ozone that's in the stratosphere. So ozone in this layer is very helpful to human beings because it acts as a layer to block all the UV light, all the energy, high energy solar light that's radiating onto the surface of the Earth. So what happens is ozone will react with the photon. Mainly, it's in the ultraviolet radiation. Then it's going to dissociate ozone into oxygen radical, oxygen, and then this oxygen will react with oxygen radical again to form ozone plus heat. Okay. So you see that ozone is basically regenerated, and what we're doing is just converting the high energy light into the heat. Okay. So we know that if we don't have ozone, then all of these UV light will shine upon the Earth, right? So for human or for animals, they're going to cause damage. Okay. So basically, the ozone absorbs UV light and convert that into heat. Okay. But later, then people realize that actually there's one species that human make that destroy this ozone layer. So this species is called the chlorofluorocarbon. So this is also called as CFC. Okay, so the CFC is very stable. So it doesn't cause problems if people inhale. It's good for inhalation, right? If people inhale these gas species, inhale the CFC is good. It doesn't cause damage, right? And more importantly, it can be used as a refrigerant. So a lot of the older fridges or air conditioners, they use the CFC as a working fluid to generate the cool air. And people really like it. And actually, CFC is not a natural gas species. So if you look at the chemical composition, it's just carbon and then decorated with fluorine. Okay? Maybe some hydrogen there, but so these type of chemicals, they don't exist by itself in the nature. It has to go through some chemical plants, and people make these materials. So this is a new type of chemical, and people really like it. It was invented around the year of 1920s. And because during that time, people normally use ammonia. So I'll just write out the chemicals. People use ammonia and sulfur dioxide as a refrigerant. We know that these species, they're very smelly, right? People inhale that, it's going to be bad for the health. So when people discover that the CFC can work as a refrigerant, they really like it because it's very stable. It's okay to inhale these gas species. It's not very toxic. But then during the year of around 1980s, people start to realize something is bad with the CFC, okay? So what happens is that when we say it's stable in the atmosphere, we're just saying that it's stable in the troposphere. That's where people live. But once the CFC concentration builds up in the atmosphere, we know that it's also very stable. So once the concentration builds up, some of them can get leaked into the stratosphere. And inside the stratosphere, the CFC is very unstable. Okay? So it's going to react with the ozone. So what happens is CFC will react with a high energy light, for example, the UV light, to form chloride. Okay. So when I write the chemicals, there are also some chlorides inside. Okay. So basically, it's a chloride that's playing a major role in this process. So then the chloride will react with ozone to form chlorine oxide and oxygen. And the chlorine oxide will react with the oxygen radical to form the chlorine and oxygen, okay? So if we look at this set of equation, what happens is the chlorine radical is always regenerated. We're not consuming any of these species, right? But what's happening is we're causing a net reduction, net destruction of this ozone molecule here, okay? So basically the ozone concentration will decrease, but the chlorine is still there. Okay, so now we know that once the CFC species gets into the stratosphere, then we're going to endlessly consume all of these ozone. And the ozone actually acts as a layer to block the UV light. So what this means is that the UV light will directly shine upon the Earth. And if human gets more of these radiation, we may have skin cancer, right? But right now, what people is observing is that we're seeing these ozone hole mainly in the polar region. So for example, here it's showing a satellite image of the ozone concentration, basically comparing two different time periods. So one is in the 1970s, end of 1970s, and one is in 2008. So this is looking at the Antarctica region, right? So this is the ozone concentration. You can see that around 50 years ago or 40 years ago, ozone concentration here is still pretty high. But maybe 10 years ago, we're seeing this large ozone hole here. So the reason why we're seeing this ozone depletion at the polar region is because the Earth is also always spinning, right? So the air is very turbulent, or it's very well mixed at the equator region. But once the CFC gets into the polar region, there's no way it can transport because the Earth always rotates in this way, right? So the air, the CFC cannot get escaped or transport back to the tropical region. That's why the CFC will get accumulated here and create these large ozone holes. And because of this issue, people realize that, well, CFC, we thought it's beneficial to human, but it turns out that it is an air pollutant, right? Because it harms the human health, animal life, threaten a lot of those things. So that's why during the year of 1990, so people signed the contract of the Montreal Protocol. Okay, so what Montreal Protocol is trying to do is people are going to ban the CFC. So all of the country over the world, you cannot use these species as refrigerants anymore. You just cannot manufacture them, right? So because of that, people are seeing a sharp contrast of the CFC concentration. So let's say here, because people manufacture so many of them, this is just showing the CFC 11, okay? So this is one type of the CFC family. And this is showing the its concentration in the atmosphere as a function of time. So here you see the unit is ppt. So ppt means parts per trillion. Okay, so you see that before the year 1990, we're seeing a steady increase of the CFC, right? So after the Montreal Protocol, people start to realize this issue, right? And then the concentration started to decrease very gradually, right? It's going to almost take forever for the CFC to drop back to the background concentration. The reason is the CFC is very stable, right? It's very stable in the troposphere. So the only way to destroy them maybe is to just let them dissolve in the ocean, right? So you see that it's very difficult to get them back. So what this also means is that CFC will still maintain at a relatively high concentration. They can get leaked into the stratosphere and then cause all of these ozone depletion problems. So we need a very long time to remediate this problem. But luckily, we realize that this is indeed an issue for the air pollution, okay? So this is one example. It shows that some species we thought may be beneficial to human being can turn out to be air pollutant as the knowledge of the human grow, right? So the other example is about the climate change. We hear a lot about these climate change issues recently. And I would say when the issue first pop out, people use a different term. So people call it global warming. Okay. So the major reason for the global warming is the emission of carbon dioxide. So then maybe after 10 or 15 years, people realize that actually the climate or the weather is not getting warm. Actually, I think in Midwest, in the recent 2 or 3 years, it was pretty cold during the winter, right? So here it shows basically we're using two different terms describing the temperature. So it's either climate or weather, okay? So weather, when we use weather, we're trying to describe the condition that's happening during a relatively short period of time. For example, 1 year or even 1 month, 1 day, right? We hear a weather forecast every day, right? We don't call it climate forecast. In terms of climate forecast, we're always talking about, let's say, hundreds or thousands of years. Okay, so when we say global warming, it's talking about climate. It's not talking about weather. But then, since people are getting confused of these two terms, then people start to realize that we cannot call this as global warming anymore. We should call them as climate change. Okay, so no matter which term we're using, so carbon dioxide is the major issue for these change of the climate, for these problems. So the reason is, let's say here I'm showing basically all different types of gas species that may be quite common in the atmosphere. So we're showing water vapor, carbon dioxide, ozone, oxygen and ozone, methane, nitrogen oxide. And this is basically showing their absorption band, right? So What this means is that, let's say for carbon dioxide, it's going to be able to absorb the radiation that's existing in this range, between 10 to 20 micrometer, okay? So we're quite interested in this bandwidth, mainly because this is where the heat exists. So we always use the microwave, right? We know microwave heats something up. So the microwave generates radiation in this wavelength, right? So what this means is that we're adding more species into the atmosphere that are able to absorb heat. So let's say if we use the Earth model again, I'll just draw it here again. Okay, so our atmosphere exists here, and this is mainly talking about the troposphere problem. So inside the troposphere, we're forming all different types of clouds, right? Clouds are able to block the sunlight, and also we have these gas species, for example, carbon dioxide. So let's say first, the UV light or the solar radiation shines upon the Earth, right? Warms up the Earth. And also because Earth has certain temperature increase, it's also going to radiate back the radiation into the universe, okay? And within the temperature of the Earth, we're going to mainly radiate back these infrared region, so these microwaves back into the universe. But let's say if we have more carbon dioxide in the atmosphere, what it's going to do is it's going to basically absorb all of these radiation in the microwave region. So that's going to, it's like wearing more clothes around the globe, right? We have more wearing, wrapping our Earth up, right? So in this case, the temperature will definitely increase. And this is talking about the climate, okay? Talking about hundreds or thousands of years. So if we know physics, if we know the radiation, we know that the temperature rise is going to be a sure thing. But why don't we see it directly? Let's say, where are we not seeing that in the Midwest? So we hear that there are temperature increases in Europe. I think last winter was a pretty hot winter in Europe, but it didn't happen in the United States. So the major reason is, although the temperature rise up, it's not going to cause a overall effect of warming up. So what happens is, let's say the ice in the polar region, after they melt, we know that if liquid melt up, it's going to absorb heat, right? Absorb heat, that's going to make the temperature cooler. So the direct impact on some region of the world is that for some regions, let's say this cold air will flow by. So for example, in some regions, then the temperature will decrease instead of increase, right? But if we just monitor the temperature all over the world, we have enough sensors, we have enough thermometers to measure the temperature. The average temperature should increase, because right now we just don't have these measurement facilities. And also it's difficult to measure the temperature over the ocean, right? So that's why we're not seeing a direct impact of this global warming. But in terms of the physics, that's how the global warming or climate change works, okay? So a very striking evidence is that we're seeing a rapid increase of this carbon dioxide. So this graph shows the time series of carbon dioxide, right? It's of this concentration, right? So it actually was measured in Hawaii. So it's measured on the Mauna Loa Observatory. Okay, so it started its measurement during the year of 1950s, and then this is the data showing up until 2018. So if you look at the concentration, it rises up from around 320 to above 400. Okay, so you see that during a short period of 60 years, how much did we increase? We increased by around 25%. Right? So this is a very striking evidence showing that the carbon dioxide concentration is ramping up. So where does this carbon dioxide coming from? where are they coming from? So we know that it's actually mainly come from the fossil fuel combustion. So of course we burn coal, right? We burn coal to generate electricity. That generates a lot of carbon dioxide, but we're also driving every day. For all different industries, they use these fossil fuel to generate energy. That's why we generate so much amount of these carbon dioxide that the global carbon dioxide concentration just ramp up very rapidly. And what this means is going to be the climate change or global warming in terms of the climate, okay? So, but if you further look at this curve here, you see a lot of zigzags. Okay, so you see the concentration increase, decrease, increase, decrease, and it's also in a pattern, right? It's not like noise taking place, right? It seems that every year we have this increase and decrease. So what might be the reason for this? I'll launch another pool. So you can take a guess. So why do we see zigzags in carbon dioxide concentration? So Morgan, are you using a cell phone or a laptop to take the class?
I'm on a laptop.
Okay, yeah. Yeah, I'm not sure. Maybe you want to update the version of the Zoom. So because I'm seeing response from other students. But can you see the shared results when I share with everyone in terms of the pool?
No.
No? Okay. In this case, I'll just repeat the question then. So after everyone finish, all right, I think we're good. I'll just end the pooling. So this question is about why do we see zigzags in carbon dioxide concentration? So there are a few options. First is the fluctuation in industrial emission. Second is instrument error. Third is the plant life cycles. And the fourth is carbon dioxide reaction in the atmosphere. Okay. So the correct answer is the third one. It's a plant life cycles in different seasons, because every year we're seeing this increase and decrease. So it of course somehow relates with the activities of these plants, right? Because during the summertime, the plants are all getting green, right? They have those photosynthesis, so they can absorb the carbon dioxide into the plant and then decrease the carbon dioxide concentration. And during the winter time, after they fade, right, we don't have those green color, we don't have the photosynthesis, the carbon dioxide concentration will increase, okay? So in terms of the fluctuation in industrial emission, normally we don't see a major difference across the season, right? And the carbon dioxide also is very stable in the atmosphere. So the reaction rate for the carbon dioxide is also pretty low. Okay, so we're going to choose the third one, plant life cycles. But you may have the question, right? So this is measuring at one observatory there, but seasons are reversed on our Earth, right? So if we're talking about summertime in the northern hemisphere, then it should be wintertime for the southern hemisphere, right? So in terms of the carbon dioxide, they should be counteract to each other, right? If you see increase at the northern hemisphere, you should see a decrease in the southern hemisphere. So theoretically, we shouldn't see these zigzags. And this is actually because of the land area. So if you just look at the Earth from the North Pole, you're going to see a lot of land area, right? So during the summertime, you're going to see more green area there. So we can reduce the carbon dioxide concentration. But in terms of the southern hemisphere, we have quite a large land area, but that's for Antarctica. There's no green area on there. So in terms of the ability to reduce the carbon dioxide, the northern hemisphere is stronger. We're going to see more photosynthesis happening there, right? That's why we can see these minor features of the carbon dioxide trend on our Earth. So people again realize this issue. So realize that we cannot keep emitting these carbon dioxide endlessly. Finally, we're going to hit to a tipping point, right? We don't know what the consequence is. We don't know how rapid the Earth system will respond. Who knows, maybe within 100 years, because of this global climate change, for example, sea level increase, a lot of the areas of the land might get affected, right? So that's why people gathered together again. So we signed this Paris Agreement, which happened in 2015. So the goal is to basically constrain, right? To constrain the temperature increase to well below 2 Celsius during this century. So basically from 2000 to 2100, we want the temperature increase to be below 2 Celsius, okay? So also, we also have some ambitious goals, right? If we can even restrain this to below 1.5 Celsius. So if we have very strong reinforcement of all of these energy policies, we should try our best to do that. But we know that the goals or the dreams are always very beautiful, right? So we also have to look at the reality. And until now, the year of 2020, the reality is that the temperature already increased by 1.2 Celsius, okay? So it's just 1/5 of the time, right? We're almost hitting to we already accomplished more than 50% of this goal. Okay? So we're not doing a very good job. And because of the energy need or energy demand, we can see further increase of this temperature. And unfortunately, that's the reality. And to solve this problem, we have to, all of the people on this world, no matter which country it is, have to unite together to solve this climate issue here, right? So this is the, actually, as a matter of fact. So that's why at the end of this class, we're also going to talk about how people plan to control the carbon dioxide. So let's say sulfur dioxide or nitrogen dioxide, people know that it's bad for human health, right? So we have those devices to collect or to remove them. So people also design devices or setups to collect the carbon dioxide from combustion. And normally that will involve more efforts, okay? So finally, let's come back to this table here. So we mentioned that for certain gas species, we actually give them 2 different units, right? So the standard can be either 9 ppm or 10 milligram per meter cube. So we mentioned that actually these 2 are equal to each other. So how do we make these calculations? How do we convert one from another? So this will involve the knowledge on the ideal gas law, okay? So if we further look at these units here, so ppm, parts per million, right? So we mentioned that they're actually mole fractions. So it's the fraction of these gas molecule among all of the gas molecules, right? So we can normally have the unit of percentage, right? Or ppm, parts per million, parts per billion, parts per trillion, etc. Okay. So for this unit, we're talking about the mass concentration, right? So it's gram per meter cube, microgram per meter cube, microgram per liter, etc. And we also sometimes will represent some concentrations of these gas species as the absolute concentration. For example, mole per liter, mole per meter cube, number per liter, right? So on and so forth. So we have to know, for this class, we need to know how we can convert from one another. And we have to use the ideal gas law, okay? So I think you guys probably have some exposure to the ideal gas law during the 2601 class. But just to make sure you know what it is, let's do another poll here. Okay, nice. Yeah, seeing all of you guys know which equation it is. So that's going to be easier. So I'll just directly jump in how we're going to use this equation here. So ideal gas law is PV equal to nRT. I know that some students also call it Pevnert, right? It's a little bit easier to memorize that. So PV equal to nRT works when it uses the correct parameter and also the correct unit. So let's say if we write it out, PV equal to nRT. So we know that P is pressure. So it carries the unit of Pascal, right? V is volume, as a unit of meter cube. N is the mole number, so number of moles for these gas species. Okay, so we can say this number of moles. So it's carried the unit of mole, right? T has the unit of T's temperature. It has the unit of Kelvin. So I have to emphasize here, when we talk about temperature, it's Kelvin, it's not Celsius. Okay, if you use Celsius and plug it in, or Fahrenheit to plug it in, you're going to get very different answers. Okay, so then the R here, so only under this situation, only under the situation when we use standard units, we're going to have the R equal to 8.314, and it carries the unit of joule per mole per K. Okay. So just for a sanity check, to make sure that we're using the correct unit, let's say, let's calculate what is a unit. Okay, so on the right-hand side, the unit is joule per mole K. We're multiplying number of moles, multiplying K. So finally, we have joule here. So on the left-hand side, we have Pascal multiplied by meter cube. All right. So in terms of the Pascal, we know that it is pressure, right? Pressure is equal to force divided by area. So basically, the pressure is going to, or the Pascal unit can be calculated by Newton divided by meter square. So if we plug it in, we're going to get Newton multiplied by meter, and that's going to be joule. Okay. So on both sides, they have the unit of joule. So that's why this equation works in this way, right? So we know that the Pevnert, or this ideal gas law, works for a gas mixture, right? We can have all different types of gases. Let's say, even for the air, we have nitrogen, oxygen, some argon, right? We have all different type of pollutants inside. Okay, so as a mixture, it works in this way. But even for a single species, the ideal gas law also works. All right. So this is talking about the partial pressure. Okay, so basically for a gas mixture, the ideal gas law also works. So the way it works is we can write out as PA B equal to NA RT. This is talking about the species A. For example, it can be sulfur dioxide, can be carbon monoxide, or oxygen, right? So the PA here is called the partial pressure. And again, V is the volume for the entire mixture, okay? Mixture, okay? NA then here is the number of mole of this species, okay? So this is the partial ideal gas law for a single species. And similarly, we can write it out as PVA equal to NA RT. So the VA here, we call it as partial volume. So the P here is going to be the pressure for the entire mixture. Okay. So how do we use this partial gas law to solve this problem? So again, if we go back to the to these different units, right? Excuse me. So let's say for the absolute concentration for this single species, if we write it out as a parameter, then it's going to be basically Na divided by V, right? Na is the number of moles for the species of A, right? And divide by the total volume. So this is absolute concentration. Let's say 1, 2, 3. 1 is going to be this one. And 2, so mole fractions is going to be Na divided by N. Na is the species A, N is the entire species, entire number of species. So the third one, it is quite straightforward. It's Ma divided by V, right? Mass concentration. So how do we convert from one another? It is actually quite easy to convert from 1 to 3 because Na, we know that it's just mass of A divided by the molecular weight of A multiplied by 1 over V. So that's going to be Ma divided by V multiplied by 1 over molecular weight of A. Okay, so we can convert from 1 to 3. Okay. And in terms of the Na divided by N, what we can do is, let's say, we still start from the first expression, Na divided by V. We know that PV is equal to nRT, right? So V, as a gas mixture, it works in this way. So V is equal to nRT divided by P, all right? So in this way, we can plug it in, Na divided by V, that's going to be nRT multiplied by P. So we have Na divided by N multiplied by P divided by RT. Okay, so we're converting from the first term into the second term. Okay, we can convert from here to here. Right, so I'm writing pretty fast, but I hope you can follow me here. All right. So in this way, since we can convert from 1 to 3, then we can also convert 3 to 1 and then back to 2. Right? So Ma divided by V is equal to Na divided by V multiplied by the molecular weight of A. And then that's going to be Na divided by N multiplied by P molecular weight of A divided by RT. So we're plugging in these series of equations all together so we can convert from one to another. So I know that it's quite fast at the end of this class. So we'll go through this derivation briefly during our next class. And finally, with these equations, we can try to convert the units from one to another. All right. So that's the contents for this class. And let me know if you have any questions. All right.